this for posterity. My writing. First thing is let's convert 50 kilometers per hour into meters per second, because we know a joule, if we think about that idea of base units, a joule is a Newton meter and a Newton is a kilogram meter per second squared, meter per second, not kilometer per hour. So let's go ahead and take 50 kilometers per hour. I mentioned so one of the other blocks that one of the things that I do to supplement my income is I tutor students, and it's usually college students studying chemistry or teachers that have to pass their certification exams, and they're English teachers that forgot all the math that they learned. So that's typically the students that I tutor. And when I show students this strategy of dimensional analysis, more often than not, students say, I wish my high school teacher would have shown me that. That is so helpful. To sort of break it down like this. And so just taking care of the units, right? We want to cancel out kilometers. We want to go to meters, and we say, well, what's the relationship between meters and kilometers? There's 1,000 meters, or 10 to the 3 meters per kilometer. So just multiply that by 1,000, and I'm in meters per hour. But I want to be in meters per hour. I want to be in meters per second. And I know that there's 3,600 seconds per hour, right? 60 times 60. So here we've set up a conversion factor where we're going to cancel out our kilometers, we're going to be in meters, we're going to cancel out our hours, we're going to be in seconds, meters per second. So 50 times 1,000 is 50,000, and 50,000 divided by 3,600 is 13.9. So 50 kilometers per hour is 13.9 meters per second. 13.9. So that's just the velocity. The kinetic energy is 1/2 the mass times that velocity squared. So at least we kind of know, okay, the velocity squared, and then we can cut it in half, and then we can start to consider, what's a reasonable mass here. So we'll take 13.9, square it. That's 193.21 divided by 2. So just the 1/2 v squared part of it gives us 96. Okay, times what here to give us one of these answers. Okay, so now we really do have to consider what is a reasonable mass for a car. Any thoughts on this? Any, sort of how would you go about it? Would you just say oh, I think in pounds the car would be this, and then maybe I'd convert pounds to, grams, and then grams to kilograms, something like that maybe, right? We need the mass in kilograms. So how many kilograms do you think is a family car? Or should we try to convert something like pounds over here? I think I've mentioned to you all before that after my first year of teaching, I studied really hard and earned my passenger and school bus endorsements with my commercial driver's license so I could take students on field trips all the time. Maybe I never shared that story with you all. I don't really remember. But my driver's license, I think, allows me to operate vehicles less than 29,000 pounds. That's like a school bus though. Okay, so a school bus is 29,000 pounds. So maybe we'll say a car is half of that or a third of that. So 10,000 pounds maybe. That seems reasonable. Okay, so let's just say the weight of our vehicle is going to be 10,000 pounds. All right. How do we convert pounds to kilograms? Here on Earth, this is an equivalence. This is not true everywhere in the universe, but here on Earth, 2.2 pounds in a kilo. Kilogram is the intrinsic property of matter, the amount of mass it's made of. The weight has something to do with gravity. So on Earth, yes, a kilogram of matter weighs 2.2 pounds, but this will not be true everywhere in the universe. Except for here on Earth, we could use it. So 10,000 divided by 2.2 gives us a mass of maybe around 5,000. It's 4,545, so 4 5 repeating. So if I say that's the mass in kilograms times my 96 for my 1/2 v squared, I get this answer 4.4 by 10 to the 5. And so again, it's really the order of magnitude that's going to sort of set this in. Like, we don't need to worry about the odd factor. Well, I got 45. Well, you know, I mean, this is like an estimate, right? So the thing is that it's in the 5th order of magnitude joules. This would be way too low, and these ones would be way too high. Okay, I think. You know, it's like, was this reasonable? Well, let's check the answer and see how well we did. So if this was paper 13 from that year, let's just queue up a new tab over here. CIU notes. And that was 2017, right? Just looking at, I think. Right here. Yes, this was paper 13 from 2017. And if we queue up the mark scheme for that, summer, right? Yeah, May, June. All right. So question number 1, what did we say? B, moment of truth here, class. Thank goodness. Okay, 1 is indeed B. I already made enough mistakes in 1 day. So that's how you go about an estimation question. Take a look at, yes. A ton is 2,000 pounds. So you could say, yeah, 10,000 pounds would be 5 tons. So what did you do after you divided 10,000 by 2.2? My apologies for being so quick to erase my work in there. So I considered the weight to be 10,000 pounds, 5 tons, right? 2,000 pounds in a ton. And so I used a conversion that I just happen to be familiar with. There are 2.2 pounds in 1 kilogram. And so when I did that division, I got like 4,545, you know, like repeating. There's just a bunch of 4 5s like that. And so kilograms are units of mass. And so I was converting the weight in pounds into mass. Like, this is something that you should know as an American, okay? Because like, we're familiar with pounds, but kilograms is what most countries use. I mean, they use mass and weight interchangeably. Like, let's say, you know, you go to the deli and, you know, Europe, and it's like, how many kilograms of, you know, lunch meat are you gonna get? Okay, even so, well, that's a unit of mass. I don't want an amount of matter, you know. So, but it's like, well, we're all here on Earth, so let's just use them interchangeably. You know, like, until we start interplanetary travel, so we're okay just using this equivalent. So, you know, the mass and the weight kind of the same thing. So I took this mass, and then remember we had calculated previously the 1/2 v squared. We're using the kinetic energy equation 1/2 mv squared. So even though it's an estimate, we're still like, you know, calculating. We still want to use the equation. We want to sort of be reasonable. So I had converted this to meters per second. It was 13 meters per second, right? 13 something meters per second, 13.9, I think. And so that was our known velocity. Like, we can actually plug in the velocity. Another idea that's embedded in this question is the idea of base units, as I mentioned, that like a kilometer per hour are not good units to give us joules, right? A joule is a Newton meter or a kilogram meters squared per second squared. Like, meters per second are embedded within this unit. So we need to have meters per second. So we did that conversion, and then 1/2 v squared was like 96, right? So if you square that and divide it by 2, you get 96. And so this number times 96, 4545.45. So times 96 gave us 4.4 by 10 to the 5 joules. So my estimate based on a 10,000-pound vehicle is like, you know, a little bit bigger than this, but we won't let that bother us. We won't say, oh, well, I chose maybe a heavier car or something like that. It's the 10 to the 5 that's the important part of the answer, right? Like that order of magnitude is more important than the odd factor up front. Any other questions about number 1 there? The diagram shows 2 vectors x and y. The vectors are perpendicular to one another. What is the magnitude and direction of vector x minus y? All right, remember we talked about how do we subtract vectors yesterday. Let's do this one as a nice review on some vector addition. Okay, so if we have vector x, and if I added y to it, I put head to tail, right? And I put it like this and I connect them. I would be adding it, but I'm subtracting it. So if this is y, what's negative y? That guy right there, right? So y is a vector that goes straight down. So this would be negative y, right? You just flip it. So I want to subtract y. I don't want to add it, which is I would put it like this, head to tail. I'm subtracting it. So I still put it head to tail, but I put negative y head to tail with it. And so here's my result right there. So here's my x vector. Here's my negative y vector. This is my result vector. X minus y equals r. Well, only in physics. What's the magnitude and direction of that vector x minus this result here? Well, they tell us this is 8. They tell us this is 6. It's going up though. I mean, we can kind of see that. So we're going to have 8 squared plus 6 squared equals r squared. Or the magnitude of r would be the square root of 8 squared plus 6 squared, 64 plus 36, 100, square root of 100, 10. So we can eliminate those two. It's not 14, it's 10. What's the angle though? Is it downwards or upwards? So it's 37 degrees. I'll tell you that right now because both of the answers have that. So we really only have to say, is it downwards or upwards from the direction of x? Well, there's the direction of x, and we can clearly see it's going upwards. Students that don't know how to subtract vectors and just maybe add them, but just go, oh, put them head to tail, do this, you know, might do the math right, but they would get this part wrong, right? They'd say, oh, it's directly downwards. So you have to flip vector y to correctly subtract it from vector x. And then it's clear to see that it's, you know, upwards from the direction of x. How do we know it's 37 degrees? If we really wanted to, we could prove it to ourselves. This angle theta here would be the inverse tangent of opposite over adjacent. And so in your calculator, you can take the ratio of those sides, 6 to 8, opposite to adjacent, 0.75, and the inverse tangent of 0.75 is 36.86 or 37. So the correct answer here would have to be B. Pythagoras' theorem, inverse trig functions to solve for the angle, vector addition / subtraction. And again, if you just think about all addition, all subtraction is just fancy addition, right? We're just adding negatives. And so really I would rewrite this as like x minus y. No, it's not, it's just x plus negative y. And then we know what a negative vector is. It's the opposite direction. And we know how to add. Put a head to tail, connect the tail of the first to the head of the last. Any questions on this one? Moving right along. That's 253. You do a couple of these, and then your brain will start to turn to mush. And we don't want that to happen before dismissal. So we'll do a couple more, but not too many. Hey, which expression using SI base units is equivalent to the volt? Voltage is one of the quantities we study when we cover electricity, electromagnetism. We haven't gotten that far yet. But see how it's the third question on this paper 1? Why? Because base units is such a foundational idea, right? Like we were introduced to base units so far, but we've never been, taught what a volt is yet. So this question is beyond the scope of the midterm. And if there are a few questions that sort of sneak their way into the midterm, and so they're kind of like freebies where I'll say, oh, look, question 4, take your best guess at that one, but I'll just tell you the answer is this. I'll give you the answer for like anyone that's sort of like this one. A voltage is carefully measured, So while we're thinking about it, voltage is the energy per charge. That's really, I mean, we kind of have a sense of voltage because like, oh, a 9-volt battery, but in physics, we have very precise definitions. And so as charges go through like a circuit, as they go around a circuit, they get energized by a source of energy. It's like a battery, a generator, the plug in the wall. That's what energizes the charges. So it's the amount of energy per charge. A 9-volt battery puts 9 joules of charge into every coulomb of charge. A coulomb is the unit of charge, named after Charles Coulomb, who did some studies with this stuff back in the 1700s. So we'll study, charges and some of the energy we've already talked about. In fact, energy is a nice concept to link a lot of the ideas in all of science, really, not just within physics, but energy is sort of a very cross-cutting idea. So it's joules per coulomb, and then we have to kind of, you can see that it turns into this sort of soup here. A joule, we know that's a kilogram meter squared per second squared, right? We've seen that before. A coulomb, though, comes from charge equals current times time, quit. So a coulomb of charge is an amp of current times a second of time. If you ever bought a battery and you've seen it, it's how many amp hours it has. An amp hour is a current times the time, just a different unit of time, and that's really telling you the charge in the battery. Like, oh, this battery has how many amp hours? It's really telling you the charge. Okay, amp hours or amp seconds are just the base units of coulomb. So this would be an amp second. Amps are base units. You may recall seconds are base units. And so we were taught all of the 7 base units, including amp, and we just kind of said, oh, we'll study that in more detail in the second semester. So the final answer here would be what? Kilogram meters squared per amp per second cubed. So choice D. And I wouldn't worry about that one so much. Like I said, anything that's like that we haven't studied, I'll either give you the equation that you need to make sense of it. So it's like, hey, we should know that the base unit of current is the amp. So here's the equation you need for voltage, energy per charge, or whatever. Charge is the constant. Or I would just say, hey, this question's no good. The answer is whatever. On a planet, a vertically launched projectile takes 12.5 seconds to return to its starting position. The projectile gains a maximum height of 170 meters. The planet does not have an atmosphere. What is the acceleration of free fall on this planet? So we'll do questions 5 and 6. And because you can see question 7 has a force versus time plot, and that's where we're getting into dynamics. So we're going to talk about that tomorrow, right? Tomorrow is our dynamics review day 3. So these questions 5 and 6 are like the 2 questions that students that sat for this paper in 2017. These were the 2 paper 1 questions they got for this stuff that we're reviewing today, right? Like it's basically 2 questions that are about the accelerated motion. And so these are sort of the relevant ones for today's lesson. Does anybody have any idea how to approach this calculation? What's the acceleration of free fall on a planet where things fall a certain time, a given height? If only there were a way to relate that, like the time it takes something to fall and the height to determine the acceleration due to gravity g. Only there were a way. If we had learned this, okay, if we were focusing on our learning objectives, if we had a learning objective that were like that, like a method to determine the acceleration due to gravity, like we find ourselves on another planet, we're like, we need to know the gravity field strength here if we're going to get off. If our rocket has enough fuel to get off of this planet, let's drop some stuff and find it. We'll figure out G, okay? This is the drop lab, right? They turn the drop lab into a question here. So we're on a planet, we got the height, we got the time it takes it to what? We launch it, let it go up and fall back down. So think about that too. It's not just as straightforward as hey, plug in that time for t and plug in that height for h, and h equals 1/2 gt squared. But if you can recognize, like, oh, that's the helpful equation. H equals 1/2 gt squared. It's got g in it. That's what I was solved for. I was given a height. I'm given enough information to calculate the time. It's the time to fall this height, right? Which is not this time. What do we need to do to this time to actually work through the calculation? Say it again. Well, we know we're going to eventually square the time, but let's read through it again. A vertically launched projectile takes 12.5 seconds to return to its starting position. So it's like we launch it, it goes up and it falls down. It took 12.5 seconds to do that. It gains a maximum height of 170. So it's like we had a little altimeter on our projectile, and it just reads once it gets to maximum height, it read off. And so we know that the height, here is 170 meters. 170 meters is the height. 1/2 g is obviously what we're going to solve for, right? These are all accelerations of free fall, meters per second squared. But what time do I plug in here? And you're all right, we got to square it in order to sort of solve it, but I don't plug in 12.5 here, I plug in what? 6.25 is correct. 6.25 seconds squared. This information here, the planet does not have an atmosphere, is the sort of permission you get to use this idea of symmetry of motion. If it takes 6.25 seconds to reach that height, it's going to take an identical 6.25 seconds to fall to give us the total time airborne of 12.5. Remember, we did a lot of projectile motion calculations where it's like, oh, we're solving for the halfway time, right? And we double that to get the total time airborne. It's the same idea, okay? Planets with atmospheres, there will be like wind resistance, and that will affect maybe its motion like on the way down. And so they're just saying, hey, we're on a planet that doesn't have an atmosphere. We got to get off. We have enough fuel to overcome this gravity field strength here. And so once we get it to this, it's just an algebra problem. It shouldn't be too tough. So I'll take 170 divided by 1/2 divided by 6.25 squared, and I get g is 8.7. Would anybody like to see any of those steps sort of worked out, or once we get to this step, is everybody good to solve for g 8.7? I'm more than happy to show any of those intermediate steps if anybody's not seeing them. So just solve this for g. Okay. The hard thing is getting that equation, right? Sort of first of all, recognizing which equation is helpful. Now, you do get, and you will get on your midterm, this data here. I'm sorry, this list of formula and this list of data. So the data is not really going to help you. Like, it's got the speed of light. If you forget g is 9.81, it's there for you. You will get this list of formula, okay? And you can see that S equals UT plus 1/2 AT squared is there. And so you just have to kind of remember that it's like S here is the displacement H, and there is no initial velocity, right? Because it's like falling from the height of 170 meters. And so it's 1/2 GT squared, where G is the acceleration due to gravity. And they even sort of remind us of that, like the acceleration of free fall here, right? G is 9.1 meters per second squared. Hold on a second. Yes, I just checked the chat there. I didn't publish it for the students inside, but I can do that. And so I want to go back to that one and kind of show all the work here. So here we said H equals 1/2 GT squared. And really what you can do is multiply both sides by 2, divide both sides by, so multiplying this side by 2 gets rid of the 1/2. So it's 2h over here. And then if you divide each side by t squared, you get that. So some students prefer to like manipulate the variables algebraically to make the thing you're solving for the subject, we say, and then plug in what you got. And it's just an easier way to start typing the calculator. So remember, the height was 170 meters, and the time was 6.25 seconds. And so computationally, it's 170 times 2 divided by 6.25 squared. See how the units are meters per second squared. And you should get 8.7 when you do that. When you multiply 170 by 2, divide by 6.25. You can plug the numbers into this, and you end up doing the same thing. You'll multiply by 2, your original half, or divide by half, multiply by 2, same thing. Divide by t squared. Got 25 minutes left in class. We're going to do one more problem. Does anybody need this working up here for a moment or two longer? I am recording these worked examples here, so I'll upload them and that way you can review them at your leisure later, if you wanted to. All right, so easy come, easy go. A displacement time graph for a toy car is shown. Yesterday, we were looking at the learning objective, students can draw and interpret displacement time graphs. And earlier today, we looked at a question here where it was like a mass on the end of the spring bounces up and down as shown. Here's a displacement time graph or a distance time graph, and we had to find the corresponding velocity time graph. So that one's worked out on YouTube for you to check out. Here we have a very similar type of problem where can we pick out the corresponding velocity time graph by looking at like what's happening with its displacement as a function of time. Okay, so we did one very similar to this earlier. That worked example is there for you. Now let's add one more. So here's something that starts in the first 2 seconds. Remember, the key interpretive idea here is that the slope of this displacement time graph gives velocity. And remember, so it's like, well, here we have a non-zero slope, a positive slope from 0 to 2 seconds. And so, and in fact, they give us numbers, right? So they've scaled the axes for us. It kind of makes it a little bit easier. So this thing rises 2 meters and runs 2 seconds. It has a rise over run of 2 over 2 or 1 meter per second. So the initial velocity is 1 meter per second. So it's not B, which has an initial velocity of 2. And it's not C, which has an initial velocity of -1. It's got to be either A or D. So that's kind of nice. By just looking at the first little bit of the motion, we can kind of conclude that its initial velocity was 1, and that's either this one or this one. Then what happens? It goes to 0, right? The slope goes to 0. So after the first 2 seconds, the velocity drops to 0, and they both do that. So we have to look further. At 4 seconds, there's a negative slope. Okay, it goes from 4, so the rise would be -4 over 2 or -2. So the velocity goes to -2 at 4 seconds. -2, this one goes up to +2. So you can see that this question is designed to capture those students who kind of aren't mindful of the negative sign here, right? We can't have a negative displacement, a negative velocity. It just means we're going in the opposite direction. So here we started at some sort of, starting point. We went 2 meters in one direction, stayed there for a bit, and then we went back to where we started and kept on going. And we were 2 meters on the other side of sort of where we started, right? We're -2 meters of displacement away. Kind of like I started in the middle of the class and I walked over to that chalkboard and walked back over through my equilibrium position to the other chalkboard, right? And that's kind of like what I've done here. And then I stay at that chalkboard for a couple of seconds. What does my velocity against time look like? Well, I have 1 meter per second and then stay at rest there for a bit, and then -2 meters per second, and then I stay at rest for the rest. So choice A seems like the reasonable answer, and it's just kind of thinking your way through that the slope of this gives the values here, right? So you're sort of matching up like this. The steepness of this part is this number here, 1, right? But the slope here is 1, so that's why it's 1, right? And so we're saying question 6 is A and 5 is B. 5B, 6A. Moment of truth. 5B, 6A. Good job. All right, we'll call it a review day there. I will give you the remaining 20 or so minutes of class to let your brain recover, or to like write some notes down or do some more practice problems, whatever you think is the best use of your time. E-learners, you are dismissed for the day. See you tomorrow. Unless you have any questions, feel free to sort of stay on or put them in the chat or unmute your mic and ask the question that you might have.